Welcome back, SPH3U. Mr. LaRusso here. We're continuing on with wave theory. The last video we left off talking about constructive and destructive interference. Well, these concepts, let's do a little quick reminder of what these mean. With constructive interference, this occurs when we have two waves that have the same orientation in terms of their pulses. So when a crest and a crest wave meet, we get interference that is constructive, which means that the amplitudes add to produce a larger wavefront. Now, of course, with constructive interference, it only occurs when the two waves, quote unquote, collide. Then once the waves finish their collision, they pass along as if the collision did not occur. With destructive interference, the opposite occurs. We have two pulses, one with a negative amplitude, the other with a positive amplitude. And when the two interact, the overall amplitude is diminished. Positive and a negative result in a smaller amplitude. And then, of course, when the waves pass through each other, they continue on as if the interaction did not occur. These concepts are kind of key to explain what happens next. So now what we're looking at something called a boundary condition. When waves encounter a boundary, there are going to be reflections. For example, here in this particular setup, we have what is called a free end reflection. And what that means is that this medium here is actually free to move versus something called a fixed end reflection. And this is where the medium is fixed down. Examples. This would be, for example, a water wave. So say a wave coming and hitting a seawall. The water itself is free to move up and down like this, where this would be similar to what would happen in, say, a guitar string, where the strings of the instrument are essentially tied down at the two ends. So the medium is not free to move. It's locked down here. With a free end reflection, when the pulse comes in, the medium is free to move up, and then the reflected wave comes back with the exact same orientation as the incident wave. So if the incident wave is positive, the reflected wave is also positive, and then comes back with the same or similar amplitude. In an ideal situation, the amplitude would be the same, but in a real world event, energy is always lost because there are leaks within a system where energy is dissipated away. But in an ideal form, the wave would come back with the exact same amplitude compared to a fixed end reflection. Now, with the fixed end reflection, something else is going on here. The medium is not free to move at this point, and the medium itself, in order for a wave to pass through, has to have some type of elasticity. So this is actually really a conservation of energy situation here. In this situation, the wave was free to move, so we can the kinetic energy was conserved, and the energy was stored in terms of a water wave. In this case, actually, sorry, not as a kinetic energy, but gravitational potential. And then it comes back, and it comes back with the same orientation. In this case, since it's not free to move here, the energy kind of slingshots and causes the wave to overshoot down this way. Kind of like a slingshot. So the energy buildup, it's not free to move here. So when it comes back down, it comes and inverts itself. And that's because of the way the energy has to be stored temporarily. And we get this inversion. Let's check out a couple of animations. So here you have the fixed end, and over here we have the free end reflection. And you can see that on the fixed end reflection, the medium is not free to move, where on the free end, it's allowed to slide up and down. So here, our medium slingshots down, so our pulse gets inverted, so our amplitude becomes negative, where the amplitude here remains positive. Now, if we send a bunch of wave pulses, we get an interesting effect. Now, if you notice, during that pulse, take a look at the amplitudes. Wind it back here a bit. All right, now we're going to pause this for a moment. Notice how the wave amplitudes are larger here. And what we're getting here is the reflected wave and the transmitted wave, they're actually interfering with each other. And we're getting constructive and destructive interference. So here you can see that the amplitudes are larger here. This means that the transmitted wave and the reflected wave are experiencing, at this point, constructive interference. We've caught it at a moment of constructive. Whereas on this wave here, the wave heights are slightly diminished. So at this point in the cycle, we're experiencing destructive interference. Let's see if we can catch it at a different spot. Now, here in this screenshot, or went a little further on in the cycle, you can see that in this fixed end reflection, we're now at a portion where we are experiencing a bit of destructive interference. But on the free end, now we're experiencing constructive interference. And it goes back and forth. So in both cases, the transmitted and reflected waves, transmitted and reflected, are going to go through series of constructive, destructive interference during the time that the transmitted wave and the reflected wave interact with each other, which is why we get this unusual pattern here where it appears that the wave is standing still. So watch again, and you'll notice if you just focus your attention here, it looks like the wave is just moving up and down, but it doesn't look like it has any left-right motion until it comes back. This is the beginning of something called a standing wave. And the phenomena of a standing wave has everything to do with what happens when a transmitted wave and a reflected wave interact with each other in such a way that they are going to interfere with each other, vacillating between constructive and destructive interference. Now, what you are seeing is this behavior on a string, but this phenomena is what in everyday life experience, what we see as, for example, a reflection. So when you see your reflection in a mirror, that is this type of wave phenomena occurring here. When you hear an echo coming off the side of a building, that is the same phenomena. Waves of all variety, whether it is light or mechanical waves such as sound, they experience reflections when they hit boundaries, and they produce these interesting types of effects. So here's that mirror analogy I was talking about. So the blue is the incident wave, and the red one is the virtual wave happening in the quote unquote mirror. And you can see in this case, this was your free end reflection. And notice how the wave comes back with the same orientation. So in a fixed end, the transmitted wave and the inverted wave, the mirror wave, are inverted to each other. So let's focus on that again. So notice this part is negative and the virtual part is positive, and we get destructive interference at this point. So in real life, there's a boundary here, and there of course isn't anything over there, but this helps to explain what's going on. So when you look in your mirror, you see a virtual image of yourself. So this is your virtual wave. So in the fixed end, the virtual wave has the opposite orientation, which causes destructive interference. With the free end reflection, however, again, this is the actual boundary. The virtual wave is of the same orientation, so we get constructive interference. So it's just another way of sort of viewing this. But the main takeaway is that when you have a free end reflection, the wave comes back with the same orientation. When you have a fixed end reflection, the wave is inverted. So the next concept of what happens when a wave goes from one medium to another medium. And again, these are examples that we see in real life. So for example, when you're looking through glass or when you're looking into water, we have an interesting phenomenon of what happens to waves. So when a wave goes from a faster medium to a slower medium, the wavelengths decrease. So if you look at the distance between wave fronts, the wave gets shorter in terms of its distance between crest to crest. In here, it's a little further. So the idea is this. So if I'm oscillating up and down like this, and if I'm moving quickly, you can see that the wave fronts are far apart from each other. So watch what happens when I change my speed. I'll keep the vertical speed constant. So if I'm moving slowly, you can see that the pulses are close together. But if I increase my speed horizontally, you can see that the wave fronts move further apart. And that's essentially what's happening. So when we go from a slow medium, our up and down vibration is the same frequency, but our x-axis speed causes a bit of a bunch up. But if I increase my x-axis speed, you can see that the wave fronts get further apart. So that's what happens when waves go from one medium to another. In the faster medium, the wavelength is longer, and in the slower medium, the wavelength is shorter. And this causes some interesting phenomena as well. When we have waves going from one medium to another, so for example, when we have wave going from a fast medium to a slower medium, we get what's called partial transmission and partial reflection. So let's take a look here what happens when we go from slow to fast. Try that again. So let's look what happens when we go from fast to slow. So when we go from a fast medium to a slow medium, we get partial transmission and then we get partial reflection. But notice that the partial reflection is inverted. This acts like it is a fixed end reflection. And the reason why that is that this medium is slower to react than the faster medium. So from the fast medium, this medium holds it back. Kind of like if this was a string and this was a chain, this would feel like a fixed medium because of the inertia of the slower medium. As a result, the wave pulse comes back inverted. But when we go from slow to fast, the second medium has no problem keeping up to the first medium. So it does not feel like there is any lag at all. So the fast medium easily keeps up with it. So as a result, it behaves like a free end reflection. So here's some animation. So that's going from fast to slow, and you can see that the partial reflection is inverted. So it behaves like it was a fixed end. And then we have partial transmission. And then when we go from, I think we need to fix that. There we go. When we go from slow to fast, going from a slow medium to a fast medium, we had no inversion. So it behaves like a free end reflection. So what are some practical examples? Here's a practical example of partial transmission and partial reflection. So this is just a random picture of a house that I found on the internet. I'm sure the owners would be really happy that they know that their picture of their home is being used in a physics lesson. But as you can see, take a look at the glass here. So you realize that at some angles you can see inside of the house. So we know that if you're inside the house, you can see outside. But standing from the outside, you can see the reflection of the sky behind you. So we've got partial transmission and partial reflection. And here's another example. And this is from a building in London. This is One London Place. Now, as you can see, this building looks like essentially a giant mirror. So you can see the clouds being reflected and you can't see inside. But the people who are inside can see outside. This looks like a two-way mirror. Well, what's occurring here? Well, at night, these aren't mirrors at all. And here's the same building, but at night, you can clearly see inside the building now. So in this case, the people who are inside have a harder time seeing outside, but the people outside have an easier time seeing inside. So what gives? All right, so here's the explanation. So let's say we're going to make a room, and we'll add a little window to our room here. Now, inside, we have a light. And then outside, we have the sun. And over here, down here, we have our observer outside. So here's the thing. All right. And, I'll use two different colors here to represent the light. So for the light bulb, I'll use this orange. So now the light bulb is producing a relatively small amount of light compared to the sun. Now what happens is only some of that light, a small amount, passes through and reaches the observer's eye. And the rest of it is reflected inside. So whoever's inside here will see a little bit of reflected glare off the windows. But during the day, the sun is very bright. So we'll do a very bright yellow. So now the sun is very, very bright and it's sending much more light inside compared to the reflected. So we can easily see the outside light because the sun is just so much brighter. But there's also a lot of reflection, and that reflected light is brighter than the little bit of light that's leaking out of the unit inside the high rise. So as a result, the observer on the ground sees this because the sunlight's reflection is so much brighter than the light that's coming out from outside of the building. But at night, our sun is gone. And as a result, the person inside the building has a hard time seeing outside, but the person outside has an easier time seeing inside because there's fewer light sources reflecting off the glass, and they can see the light from inside the building. So as a result, if you're inside a building, and if you've ever tried to look outside, most people know that they have to go right up to the glass and cup their hands around their eyes to block out the external light coming from inside the house so they can see outside the window, or they have to shut off the lights inside the house in order to clearly see outside. So that's why during the day, the building looks like a mirror, and at night, you can totally easily see right through. Okay, so now the next thing on the agenda is we need to talk about standing waves. So in order to talk about standing waves, we need to talk about resonance first. All right. So what is resonance? Well, resonance is a specific frequency or frequencies which all systems naturally want to vibrate at. So an example of this is a childhood swing. Now, when you're a little kid, and most little kids know, they figure it out, that when you're on a swing, let's make a little swing set here. So here's the rope. So we want to get the swing to rock back and forth this way and this way. Every little kid knows that you have to lean back and kick your feet at the exact right time in order to get the swing to start oscillating back and forth with increased amplitude. If you don't get the timing right, the swing just won't oscillate like the way that you want it to. So resonance is a specific frequency or frequencies that the minimum amount of energy input produces a maximum output. So there are lots of examples. So resonating, a kid on a swing. Every musical instrument is based on resonance. So when you pluck the string of a guitar, that is another example of resonance. And we get the strings naturally want to vibrate at a specific frequency based on the length of the string, the density, and the tension on it. All right, so let's take a look at a practical example. Here's a bass guitar. So this is an example of a system that naturally wants to resonate. So if we look at this end, we have a guitar, we have the bass string, and here, that's considered a fixed end. This is called the nut of the guitar. And down here is the bridge and is also fixed. And then when I play the note, you can see the string vibrating back and forth. And it makes a particular tone. Now, if I go to the next string above it, and keep going, we get different notes being produced. All right, so I can actually lower the tension even further to get even more of a dramatic effect where you can see the string vibrate in a specific way. Now, when I do it, you can really see how slowly the string is vibrating back and forth. So you can really see, and if you look at the end here, no wave energy here. And down here, same thing. So these are fixed reflections, fixed end reflections on both ends. And you can see I'm not doing anything special. I'm just plucking the string and it naturally wants to vibrate at that frequency. If I lower the tension even further, it vibrates even more slowly. If I increase the tension, you can see that it vibrates much more quickly. And you can hear it by a different sounding note. So there's another practical example of resonance. So let's investigate this phenomenon a little bit further. Now, with resonance in a guitar string, as I mentioned before, we have two fixed ends. And the pattern that gets generated in the guitar string is related to the transmission and the reflection of these waves. So if we take a look, the green wave is moving in the forward direction. And then the red wave represents the reflected wave. So if we notice at this point right here, we are constantly getting destructive interference. There is no amplitude here. And if you look at the wave and we look at the dividing line, you'll always see that the green and red wave are always equidistant from this line here. I'm going to pause it at any moment here. So when we take a look, and this is how we can tell we're going to have destructive interference. Look at the amplitude of each of these things. The amplitude of the reflected wave versus the amplitude of the transmitted wave. Equal amplitudes, opposite direction. And you'll notice that at every spot where we have destructive interference, we get the same phenomena. The amplitude of the green, the amplitude of the red. They cancel each other out. Same over here. In this case, the amplitude of the red, the amplitude of the green. Opposite amplitudes, positive, negative, equal, cancel each other out. So we get a resultant of zero. But let's take a look at these regions where we are having constructive interference. There's constructive, there's constructive, there's constructive. The amplitudes reinforce. So the amplitude of the green plus the amplitude of the red, if we add those two together, we end up getting constructive interference. Now, the designer of this particular demonstration obviously didn't mathematically make this look exactly the way it should have been, because this amplitude plus this amplitude, the black wave should have stopped about there, but that's not really a big deal. But you can see that we have constructive interference because both the green part of the wave and the red part of the wave are positive. Down over here, same deal. The amplitude of the green wave plus the amplitude of the red wave, and you get constructive interference. So as this cycles through, I'll try to stop it at the exact spots where we get destructive interference right there. So here, if you take a look, it's all destructive interference everywhere. So positive, negative, destructive interference. Positive, negative, destructive interference. Well, 0 plus 0 is still 0. 1 plus negative 1 is 0. 0 plus 0, 1 plus negative 1, 0. The amplitude all throughout here is going to be 0. So the entire thing is destructive interference. And at this point in the cycle, here's where we are getting constructive interference. Now, if we take a look, you can't see the green wave because it's behind the red one, but we have maximum constructive interference because positive 1 plus positive 1, positive 2, negative 1 plus negative 1, negative 2, positive 1 plus positive 1, positive 2, so on and so forth. But if you notice, at these points here, and let's highlight these with a different color. At these points here along the dashed lines, the amplitude is always 0 here, because either we have destructive interference, perpetual destructive interference, or we get 0 plus 0. No matter what, we always end up getting no amplitude here. However, in these regions here, in between, we can get both constructive and destructive interference. We have a special name for these. These areas are what we call antinodes. And these spots here, we call these nodes. And technically, we have nodes at the end. So where we have nodes, we never have wave amplitude. The amplitude is always at its absolute minimum. But in the regions where we have antinodes, we go from positive constructive interference, negative constructive interference, and in between, destructive interference. And that's why it looks like a standing wave. So in the regions where we have antinodes, we go from constructive interference to destructive, to constructive, to destructive, constructive, so on and so forth. And if the frequency and the lengths and all the other parameters are right, it appears that the resultant wave, which is the wave that is colored black, it appears to be standing still. But in reality, there are two waves that are interfering with each other: the green transmitted wave and the red reflected wave. And it produces this particular pattern. So let's apply this idea to the guitar string. So here on our guitar, there's a node, there's another node, and right here in the middle, we have our antinode. And we can see that we're going from positive constructive interference. Down at the bottom is negative constructive interference, where the two negatives add. And then when it crosses the equilibrium, destructive interference. So constructive, destructive, constructive, destructive, constructive, so on and so forth. Now, this particular mode of vibration, this is called the fundamental, or the first harmonic. So it's called the fundamental or the first harmonic. And in any fixed both ends system, this is the lowest possible frequency that we can get resonance. But there's more than one resonant frequency. And in fact, you can keep on subdividing it. Now let's take a look at what's called the second harmonic. Now with the second harmonic, where there once was an antinode, is now replaced with a node. And in between, we have two antinodes. This here is called the first overtone or second harmonic. So let's take a look at the pattern here. And the pattern I want to show is this. Second harmonic, look how many antinodes we have. So let's go back to our first harmonic. And when we go back to our first harmonic, we're just going to count antinodes. So first harmonic, one antinode. Now let's jump to the second harmonic. We have two antinodes. So second harmonic, two antinodes. Let's take a look at the third harmonic. Antinode, antinode, antinode. So with the third harmonic, we get three antinodes. And you can see the pattern continuing on. Fourth harmonic, 1, 2, 3, 4 antinodes. Fifth harmonic, 1, 2, 3, 4, 5. Sixth harmonics, 1, 2, 3, 4, 5, 6 antinodes. And that is what we have modeled here. So with our first harmonic, one antinode, second harmonic, two antinodes, third harmonic, three antinodes, etc., etc. So this is fixed both ends. Well, There's also another type of resonant system, and these are air columns. So for example, something like a flute. In these cases with resonant air columns, if it's open at both ends, it's the exact mirror of the fixed both ends. Let's take a look. Node, antinode, node. All you do is if it's open both ends, everything's flipped. So instead of having nodes at the ends, we have antinodes. Same with this. Node, antinode, node, antinode, node. It's just the reverse. But the takeaway from this is how much of a wave we have here. Well, when we take a look, let's take a look at a sine wave. When we draw a sine wave, a full cycle of a sine wave is this. But then if the reflected wave is the exact opposite, we then get this pattern right here. So if you look, one antinode is equal to half of your wavelength. So the distance from node to node is always equal to a half wavelength. So in this case, we have a half plus a half, 2 halves lambda, second harmonic. Look at the numerator, 1/2 first harmonic. All right, 1/2 plus another half plus another half. That's 3 halves lambda, third harmonic. And then 1, 2, 3, 4 halves. 1, 2, 3, 4, 5 halves, fifth harmonic, so on and so forth. So the takeaway between node and node is always equal to half lambda. That's also true if we go from antinode to antinode. That is also equal to 1/2 lambda. But what happens when we have what's called fixed one end? And what's a fixed one end? This is an example of this would be a pendulum. So a pendulum is basically a mass that swings back and forth. This would be considered the antinode, and this would be considered the node. And in this case, the distance from node to antinode is only halfway, because we know that from node to node is half wavelength. So therefore, from node to antinode has to be a quarter lambda. So in this type of system, this type of resonant system, we have to have a node here and an antinode here. That's why it's only equal to 1/4. So here is an example of fixed one end. So the first harmonic, which is represented by the resonating black line here, in this case, it's going from node and we have one antinode. And this distance is equal to 1/4 lambda. Now let's take a look at the next harmonic. We're always forced to have a node and an antinode. But the rule is it always goes node, antinode, node, antinode. You can't have 2 nodes in a row. So we have to go from node for the next mode of vibration, antinode here, and then a node here, then an antinode. And then what you can see here is that we have with the red resonating wave, here we have 1/4 plus another quarter plus another quarter. So that equals 3/4 lambda. So our first one was 1/4 lambda. Then we skipped the second harmonic and we jumped right to the third harmonic. Now let's take a look at the next one. Again, node, antinode. So in this case, drawing out where all the nodes are, and in between, antinode, 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 and antinode. So counting the halves, first of all, from node to node, we know that's 1/2, 1/2, 1/2, 1/2, and 1/4. So we've got 1, 2, 3, 4 halves. So 4 halves plus 1/4 is equal to 8/4 plus a quarter, and that's equal to 9/4. So in this particular demonstration, they jumped right up to the 9th harmonic. So again, let's take a look at the static version. So node, node, antinode. So still node, antinode, but so now we count the nas. The first harmonic has 1 na. The next resonant frequency, which happens to be the third harmonic, has 1, 2 nas and 3 nas. This gives us our 5th harmonic, so on and so forth. So for an additional explanation, and this is a pretty good one, great hair too, click on this link in the OneNote and you can actually see a very, very well done explanation with visual demos of standing waves. So this one is pretty great. Gotta love those physics nerds, eh?